independent and self-contained. So if you get lost for the first work, it's totally fine because these are independent of the other two works I'm going to introduce. Okay, so the second setting is about information design in linear model. Okay, I think I'm not the best person to present this work in this room because this is Nika's paper. Yeah, so I think Minda is not here. Okay. Yeah, so in this paper, they consider a totally different model, and it's a more abstract model. We still have K agents, and each agent has to complete a task. And we use a collaboration network to model the relationship between the agent's tasks. So we have nodes. In this network, we have nodes, and every node corresponding to an agent. And every agent will choose their effort of completing their task. So their strategy is denoted by theta I as a real value between 0 and 1. And so this is an abstract model, but if you consider this problem in the collaborative learning setting, you consider this theta I also represents the normalized version of the contribution level. Or you can also consider some other settings where everyone has to complete some computing task, and this theta I denotes the effort when they perform the computing tasks. And we consider an even more simplified setting. That is, the quality of agent-size task can be represented as a linear function of the effort contributed by anyone. That is to say, for the benefits to agent I from other people is linear. So for the quality of agent-size task, it's a summation of agent I's own contribution plus the weighted sum of the contribution from other agents weighted by W sub ij. Well, this Wij captures the similarity between the task done by agent I and agent J. So this can give us a model of a weighted. So this just gives us a weight on the edge between I and J. So this gives us a weighted graph to model this collaboration. And so this linear structure sounds a bit abstract, but it still captures some structure of collaborative learning without inductive bias. So what I mean by no inductive bias. So in the first work, when we talk about collaborative learning, we assume there is a hypothesis class, and the labeling function is in the hypothesis class. And here we just consider that the labeling function can be anything. And then given instance space X, and again, we assume that they are labeled by the same ground truth function. And every agent has a distribution, every agent I has a distribution Qi over the instance space. And then the theta I denotes the number of samples. And so then when the input space be large enough, they goes to infinity, then agent I's accuracy can be written as a linear function, as a summation over all agents and a summation over all data points of Qi of X and Qj of X times theta J. And by using this inner product of Qi and Qj, it represents the similarity between the distributions Qi and Qj. And so this formulates the weight Wij in this linear model. So this linear model still captures something in the collaborative learning. And go back to this model. For every agent, its objective is to achieve the quality of its task, the quality of the task greater than 1. So this still captures the.
Is weight side positive?
Yes.
Always positive.
Yes, I think so. Yes. Yeah. So this setting is still share the same structure as we did like in the first work. Like every agent have some learning objective, and they just want to make sure that their objective is satisfied. And in practice, before we move on, let's consider the role of a platform. So in practice, usually for the collaboration, there are a lot of agents. And it's hard for the agents to have a global knowledge about who they are collaborating with, how much other agents contribute, and to what degree the effort of other agents improve the quality of their task. So they just have no idea about like what other theta j, and also they don't know like where their position is in this collaboration network, and maybe they don't even know what this. There's just a lack of information about this collaboration network. But collaboration platform has more knowledge. Like they have a better knowledge about the relationship between the tasks, so they have a better idea about how this collaboration network looks like. And then how much an agent knows about their neighbors depends on the designs of the platform. That is to say, the platform can decide how much information, what kind of information they want to release about this current collaboration.
I have a quick question.
Yeah.
So do the agents have any like prior over this network, or
Yes.
do they know absolutely?
Yes, they have prior. Yeah. Yeah, we will get to like Basically, they just know that they have equally chance at any place in this network, but we will get to that formally later. Okay, so no matter what kind of information is shared with agents, we can define we can define the feasibility of the collaboration. So we say a collaboration theta is feasible for agent I if the expected total effort is above threshold. That is to say, in expectation, the quality of their task is greater than when their objective is satisfied. Here, the expectation is taken over the randomness of. They have some prior, so then they got some information. So there is some randomness in their belief about the collaboration, and the expectation is taken over that randomness. And we say a collaboration theta is feasible if it is feasible for all agents in that neural network. So for example, if we just consider this line graph with 3 nodes, and suppose the agent has a full information. As you say, they know the structure, they know where they are, and they know what others will contribute. Then this is solution 0.6, 0.4, 0.6 is feasible because everyone can have their quality to be greater than 1. But if theta 2 is 0, then this is infeasible because agent 1 and agent 3 are the expected quality is 0.6, so it's below 1 now. And again, a solution is stable for agent I if the agent I doesn't want to change their effort unilaterally. I should say, for agent I, theta I is the minimum effort for them to contribute to satisfy their constraint. And we say a solution theta is stable if it is stable for everyone in the network. And go back to this example. And this is not a stable solution because agent 2 can lower their contribution without violating their own feasibility. So there are some stable solutions. Any idea about like what are the possible stable solutions? Okay, you can either have the
0.5 for everyone because the threshold is 1, or?
no, if it is 0.5, 0.5, 0.5, then agent 2 will still deviate. Yeah, so it can be either agent 2 contributed 1, or agent 1 or agent 3 contributed 1, and agent 2 contributed 0. Okay, so then go back to this central topic. the tension between efficiency and the stability. How much efficiency is lost due to this stability? So we can define optimal feasible solution. Just consider the solution which minimizes the total effort such that this among all the feasible solutions, and the optimal feasible and stable solution by adding another additional stable constraint. And then they show that the optimal solution and the optimal stable solution can be far away from each other. And indeed, it can be very bad. That is, the stable solution can be k times worse than the optimal solution under both full information and no information setting. So this, okay, yeah, maybe it's, okay. So, and this gap of k can be observed in a very simple structure called double star network. So in this network, there are two centers that can represent like some very powerful agents, such that if they did their work, their effort can help like half of the leaf agent set connected to them. So we have two centers and k over 2 minus 1 leaves on each side. And we consider unit weight graph, so every edge has weight 1. And in this structure, the optimal solution is 2. So we only need the center to contribute 1, and then the leaf doesn't have to contribute anything. And but for the stable solution, when the agent have the full information, so they know exactly where they are and how others or what others contribute, and then the stable solution has to satisfy either all leaves contribute 1, or like one center contribute 1, and for the other part the leaves contributes like everything. So the stable solution has to suffer linear in k, has to contribute linear in k. So why this is the case? Because in a stable solution, there is no way for both centers to contribute 1, because they are connected. So if both contribute 1, then at least one of them will definitely deviate. And once the center deviate, then the leaves connected to this center has to do all the work. So this makes a stable solution has to do like k times more work, and it makes it very inefficient. So these are in the full information setting that agents knows everything about this collaboration. What about the agent have no information? Well, in this case, all agents have to contribute a constant effort, so it will still lead to linear in k cost.
So by no information, you mean they don't know where they are in this graph?
Yes.
Not just that they don't know what others are doing.
Yeah, they don't know where they are. Because when they don't know where they are, basically all the agents are symmetric, so they will contribute the same amount. So by considering everyone consider the same amount and then do the calculation, everyone has to contribute a constant number of effort. So in total, they will also incur linear in k cost. So lack of information will also bring some barrier for the efficiency. So we have an efficient but unstable solution, which leads to the total effort to be 2. And for stable solutions, if the agent have full information, the total effort will be linear in k. If agent had no information, it will also be linear in k. But linear in k is really bad thing, because if they don't collaborate, the total effort is also linear in k. That is to say, in this kind of collaboration, it just doesn't bring any benefit in this collaboration. And so platform, now we want platform to leverage their information advantage, and by selectively revealing some information about the agent's locations. But then the main question that they try to solve in this paper is about what's the right amount of information. And the positive result is that by releasing the right amount of information, they can improve the solution to the square root of k. So about information design. So far we haven't talked about like when we say design information, what does it exactly mean? So let's go back to the paper by Kamenika and Gosko in 2011. They proposed this thing called information design or Bayesian persuasion. So here is a simple example in this 2011 paper. So consider a game between a prosecutor and a judge. And a judge have to choose to convict or acquit a defendant based on a signal chosen by the prosecutor. A judge must choose whether to convict or acquit a defendant. And the judge will receive utility 1 by making the right decisions, and utility 0 if they make the wrong decision. And the prosecutor always prefers conviction regardless of the state of the defendant. So, and both parties, both the judge and the prosecutor, they know that 70% of the defendants are innocent and only 30% of them are guilty. So they share the same trial, that is, the probability of guilty is 0.3. Then the prosecutor conducts the investigation and is legally required to truthfully report the outcome of the investigation. With no information, like the prosecutor just did nothing about this investigation, and then the judge will always acquit because only 30% of the defendants are guilty. So the best action for the judge is just to acquit everyone if they only have this prior information. And with full information, the judge knows exactly the state of the defendant. Then the judge will convict with probably 0.3. But now, the prosecutor can do something. They can design some signal scheme. So they do the investigation, and then they will signal the judge by using this correlated random scheme. That is, if the defendant is innocent, then with probability 4/7, they will send signal I to the judge. Otherwise, they will send out signal G. And if the defendant is guilty, they will send the signal G to the judge.
Sorry, I didn't understand what's full information in the previous slide. What's the information?
Oh, that means the judge knows exactly if the defendant is guilty or innocent.
Oh, so it's not information prosecute. It's like some oracle all.
Suppose the prosecutor just do the full investigation, so they just exactly know what the state of the defendant.
So the prosecutor always knows all the information about a defendant, and
Yes.
it's really just about how much of it he tells to the judge.
Yes.
So then the probability is 0.3 over multiple defendants.
Yeah, suppose there are a lot of defendants, and we just basically know that the prior knowledge you have is that only 30% of them is guilty. So you can assume that for every defendant with probably 0.3, they are guilty, and with probably 0.7, they are innocent.
Okay, so we're only looking at average rates over some population of defendants here then.
Mm-hmm.
Okay.
Okay, now we define then the prosecutor can run this signaling scheme.
Isn't this Bayesian? So
Yes.
Okay. So
Yes.
it's not over a population, right? Like it's for.
Yeah, it's some Bayesian prior. Like for every defendant, you just with probably 0.3, they are guilty. It's your Bayesian prior over the defendants.
No, but in the full information setting, what does it mean?
Oh,
What is the probability
yeah.
0.3
So
for?
they are guilty with probability 0.3. So when every agent comes, they sample their state from this distribution, and the prosecutor decide if they reveal the state to the judge, and if they reveal the state, then it's full information. Yeah. Okay. So now consider this random signaling scheme. When observing the signal I, the probability of guilty conditional on I is 0. So when observe this signal, the judge will acquit. But when observing the signal G, the conditional probability of guilty, the probability of guilty conditional on the signal G is 0.5. Well, assume that the judge will break ties by conviction, because we can always just slightly perturb this signal scheme so that this conditional distribution is 0.5 plus epsilon. So in this case, every time we observe the signal G, the judge will convict. And then the judge will convict 60% of the time. So that is to say, the judge will convict with probability 6, even though she knows that 70% of the defendants are innocent, and they fully understand the prosecutor's incentives, and they also know that everyone is telling the truth and nobody tried to lie here. So that is the power of signaling of information design by playing with this Bayes rule. Okay, so now go back to the data sharing. There is also some information asymmetry in the platforms. So what exactly the information is known to everyone? So suppose that the structure of the graph is known to everyone. That is to say, everyone has a shared understanding of the natural task in the setting. So they know that, okay, so if the collaboration structure is like a double star, then the agents know that it is a double star. The platform has full information. So then they know which agent is at which location on this graph. And agent has minimum information. So each agent is equally likely to be any node in this network. That is to say, the agents are mapped to the nodes via a random permutation. And the permutation, the realized permutation is only known to the platform, but not to the agents. And then we can design a signaling scheme using Bayesian persuasion. So they have a pre-committed, credible signaling to shape agents' posterior beliefs. And so this signal scheme will map every permutation to a joint distribution over the signals. And then just using this using these randomized signals, we reveal partial information to the agents, and then induce this correlated belief using this correlated randomness. And due to the revelation principle, the space of the signal just need to be the same as the strategy space. And basically, when designing this signal scheme, the signal sent to the agent just need to be the recommended effort level, and that is already sufficient. And they call it direct signaling scheme. And then we want the signaling scheme to be persuasive. That is to say, when they receive the signal, the best thing for the agent to do is just to follow the signal, because the signal is exactly the recommended strategy, the recommended contribution level, the effort level. So formally, that is to say, for any alpha, when the agent I receive the alpha, and also assume that everyone else will follow the recommendation, then the best thing for the agent to do is also follow the signal, follow the recommendation. And then the platform's goal is to design a persuasive signaling scheme to minimize the expected total effort. That is the expectation over the total, the sum of the signals, which is exactly the recommended efforts. So still go back to this double star example. As we mentioned before, there are two solutions. One is like ask centers to do all the work, which is efficient but unstable, or ask leaves to do all the work, which is stable but not efficient. And then we can design some signal scheme. So the signal scheme in this example is with probability 1 minus p. So once the platform draw the permutation, then with probability 1 minus p, they will send signal 1 minus epsilon to the centers and 0 to the leaves. And in this case, if the center decided to follow 1 epsilon, well, then they will over-qualify because both contribute 1 minus epsilon, so is above so their quality will be like close to 2, which is a constant bigger than 1, which is what is ideally they want to achieve. But with very low probability, the platform will send the signal 1 minus epsilon to leaves and 0 to centers. And in this case, upon receiving the signal 1 minus epsilon, if they follow 1 minus epsilon, the nodes will slightly underqualify, because if all the leaves contribute 1 minus epsilon, it is not sufficient to achieve the quality of at 1. So by picking the right choice of p and epsilon, these two can cancel, and then which makes the best solution for the agent when they receive the signal 1 minus epsilon is to follow. It will help them to achieve exactly the expected quality to be at 1. And also in this case, because with high probability, we will have the centers to do all the work, and with low probability, we will have leaf to do all the work. So the total expected cost will be in the order of the square root of k instead of k. So which makes the collaboration more efficient. So yeah, so that is a signaling scheme in this special case of the double star graph, but they have very general results in this paper. Like for any unit-weighted network with k nodes, yeah, they just use this. They have a binary persuasive signaling scheme such that the cost is square root of k times the optimal cost. And also they show that the square root of k is tight. And they also have results for the more general graph types, so this is for the unit weight, but they also consider general weights, and also can achieve results better than linear in k. Yeah, I think that's for the information design in this linear model. Okay, so I think now we should get to the third part. Any questions for the second part? Okay, good. So now both works only consider the contribution levels. And what about beyond the contribution levels? That is, what about they can fabricate data? And we have the question of if the agent can fabricate data, can we still incentivize truthfulness? Can we still have them report their data truthfully? Well, it is usually hard to detect the fabricate data, but it is possible in the homogeneous setting. So we get into the third paper, data allocation in normal mean estimation. So in normal mean estimation, we want to estimate the mean of a Gaussian distribution with no variance. And suppose if we only have one agent, the agent collects m samples at a unit cost c, and the agent wishes to minimize its penalty, which is estimation error plus the cost of data sharing. So penalty is just a negative utility. And in this Gaussian mean estimation, this penalty can be written as a sigma square divided by m plus c times m. So when the agent has to work on her own, the agent will then collect a sigma divided by square root of c samples to minimize the penalty. But when we have k agents, they collect the data and they share their data. So they have, when I say homogeneous setting, I mean all the K agents will have the same data distribution. And now they want collaboratively to estimate the mean. So for this problem, to measure the efficiency, they consider a slightly different notion, but yeah, just consider a total penalty of all agents. And if they collaboratively to collect total amount of points, then the social penalty will be the summation over the penalty of all agents. That is the estimation error times K plus the C times the total amount of data.
Why is there a K in the estimation? Why is the K being multiplied? Don't you give everyone the same?
Oh yeah, the estimation error is the same for everyone, but the social penalty is the total penalty of everyone. So everyone will suffer this penalty once. So for then in total there will be K times this amount. So to minimize the total penalty, the social penalty, we want to collect this amount, like sigma times the square root K divided by square root of C amount of data. And but we're in a collaboration, so the agents can split the work, and everyone just need to collect sigma divided by square root of C times T points, and then they can obtain K times more points by getting the data from other people. So collaboration can benefit every agent, because if they work on their own, then their penalty is 2 sigma times the square root of C. But if they work together, they will reduce their penalty by a factor of 1 over square root of K. And now consider mechanisms. So if we don't want to do any design, and we just ask agents to contribute data, and we pull the data and share all the data we collected with everyone, then selfish agents can improve their penalty they can reduce their penalty by half by contributing nothing, because when the number of agents is large, one agent doesn't share the data, doesn't change the estimation error a lot, but they can just reduce their contribution, their data sharing cost to 0. And but then what if we just still do pool and share, but we only give the data to the agents when they contribute enough data? Then selfish agents can fabricate data. So in this paper, they want to consider that how to design a mechanism to incentivize agents to share enough data and also report their data truthfully. So we model the mechanism. So a mechanism will receive a data set from every agent and then returns an allocation to every agent. So here, allocation can be a bigger data set, saying all the data set so they can send the data from all the other agents to agent I as allocation. And after the mechanism is published, an agent I will collect MI points xi, but only submits a modification of xi saying yi. So this submission function fi will map the true data set to a possibly altered one by fabrication, and it doesn't necessarily have to be of the same size. Then on receiving her allocation ai, the agent I can estimate the mean by an estimator hi on the which is a function of the true data set and their fabricated data set and their allocation. So in this model, an agent strategy space has 3 parts. That is, the amount of data they want to collect, the summation function, that is how they modify the data, the true data set, and the estimation function about like once they have their data and they receive their allocation, how do they estimate the mean? And the agent penalty is the same as we mentioned at the beginning, the estimation error plus the data sharing cost. And again, to make the problem well-defined, we still consider the worst-case error by taking this premium over the true mean. Then they propose a incentive-compatible mechanism in this work. The high-level idea is send the agents high-quality data only if the data they share is of high quality. So how to measure the quality of the data they share? The mechanism can measure the quality of the data they share yi if she knows the true mean mu by looking at the difference between the mean of yi and mu. But now, even though the mechanism doesn't know the true mean mu, but she can still estimate it from others' data because now all the agents have the homogeneous data sources. So if all the agents share their data truthfully, then we can still have a good estimation of mu based on the data shared by other people, and then measure the quality of the data shared by agent I. So the mechanism they propose is for every agent I, they look at the data shared by other people, not agent I, and then they first randomly sample sigma divided by C times K, this amount of data from all the other submission. And then they look at the mean of the data shared by agent I and the mean of this randomly sampled data points, and set a noisy invariance to scale with the difference to be the square of the difference between these two means. And then for the remaining data points submitted by other people, they just add a noise to this data. Well, the noise are scaled with are sampled from the Gaussian distribution with the noise variances here. And then the mechanism will send the data, this zi, which is not corrupted, and the zi prime, which are corrupted by adding this the noise at this level, and they just send this data to the agent. So if the agent fabricate data, then it's very likely that the mean of their fabricated data is far away from the mean of the data shared by other agents, and then the noisy level of the I prime will be higher. So then the agent will get receive the allocation which is more noisy. So that is a high-level idea about this mechanism. And then the mechanism will recommend every agent to follow a strategy. S star I, well, the MI is the exact amount that in the optimal collaboration they want everyone to contribute. And the summation function F sub I star is the identity function, which means truthfully report your data, and don't fabricate. And then let the estimation function to be the weighted average, while the weight is reduced for the corrupted data. So the recommended strategy from the mechanism is to collect a sufficient amount of data submitted truthfully, and then use a weighted average estimator. And then in this work, they prove that this strategy as a star is stable. That is, for every agent I, they have no incentive to deviate from this strategy, so that they better collect this MI star amount of data and not fabricating the data. And also, this S star is individual, rational, and efficient. So, so I think the most interesting idea about this incentive compatibility is about they can, using this homogeneous assumption, by enforcing everyone to truthfully report their data. So here is some proof sketch of the incentive compatibility. So basically, they want to show that there is no for agent I, she has no incentive to deviate from S star sub I to another strategy S sub I. And so for every strategy, it has three components, MI, FI, and HI. And so they decompose the proof to two parts, that is, for any MI, for any sample size, submitting the data truthfully and using the recommended estimator minimize their penalty. That is, if you fix MI, then FI star and HI star is the best thing for the agent I to do. And step 2, the agent's penalty is minimized when she collects M star sub I amount of data. If they report truthfully and using estimator H star I. So for the step 1, to prove that the best thing for them to do is using F star I and H star I. Well, if we just write down this penalty explicitly, it's just basically trying to show that this combination of H star I and F star I can achieve the minimax risk for normal mean estimation. So they just use some tools from a simpler so basically they use some recipe which is about minimax normal mean estimation. So consider a simpler setting. Well, we just have some ID data points from a Gaussian distribution, and they want to show that the minimax risk is sigma squared divided by m. And what it can do is, for the upper bound, you can show that by using the estimator, just to take simply take the mean of the data points, it can achieve this minimax risk. And also, they can lower bound this via Bayes risk by choosing a prior gamma by choosing a prior and suppose that mu is sampled from a prior. And then for any estimator, the minimax risk is lower bounded by the Bayes risk. And then because then conditional on the data points, the mu is a Gaussian, and then they can show that by choosing H being the posterior mean, this quantity is minimized, so that they can show that the minimax risk is sigma squared divided by m. So by combining this, they can show that by using, in the ID setting, by using H being just simply average, they can achieve this minimax risk. So now, in their setting, they want to show that the combination of F star sub I and H star sub I can obtain this minimax risk. And they just use the same recipe because F star I and H star I are explicitly defined, so they can calculate the risk achieved by F star I and H star I and they define this as a minimax risk. And then you also use the Bayes risk, like construct a prior over mu and showing that this is also lower bound the minimax risk. And then they can show that F star I and H star I obtain this minimax risk. But by applying the method in this method, there are two subtleties. That is, it's not just about estimator HI, but also about the submission function Fi, which makes the problem much more complicated. And also, in this recipe, we consider the data ID, but in this setting, the data available to agents are not ID anymore, because the noisy level of the I prime depends on Yi and the I. So they just by doing a lot of math, we can, and following the same recipe, they can show that F star I and H star I can obtain this minimax risk, and show that F star I and H star I is incentive compatible. So the agency better tell their data truthfully. And then computational, the agents will use F star I and H star I to show that M star I is the best thing for the agent to do, that is contribute this amount of data. And the idea is that they show this function is convex in MI. And by choosing the right level, by choosing a specific choice of parameter alpha, they show that this is minimized at M star I. So they prove that this strategy S star I is incentive compatible. That is the best thing for the agent to do. So agents have to, they better share their data truthfully, and they better to collect enough amount of data. So that's all the technical idea about this.
So intuitively, what is happening here, I don't think I can understand what precludes the following scenario. Like I see some samples, I artificially sharpen them up towards the mean by like projection sampling things on the tail, reporting that, but then I claim that the estimator I'm going to use is just MLE maybe. Like what is happening here that, like what exactly is happening in the math maybe that avoids?
I think it's okay to do that. I think the thing only matter here is empirical mean. I think if you fabricate data but with the same empirical mean, I think it doesn't hurt anything.
But okay, so here
But it also doesn't improve the utility. So they might have the same utility.
Okay. Here you're not getting. So you're not receiving payments here, right? You're
No,
just,
no.
There's a cost model, and then. But if I were receiving payments, then potentially, maybe I just give a sample which is much lower variance, but same mean.
Yeah, but I think for here it's still okay. But does it really matter? Because I think for the platform, they don't care if they just care about the empirical mean, and they don't care about the variance, or like if they are really the original data. I think if they just make the empirical, they fabricate data, but with the same empirical mean, I think it doesn't change anything here.
Yeah, I didn't fully understand that part also, because like why is there no bias variance trade-off there on the server side?
Because I think even for the platform, they also when they do the calculation, everything only depends on the empirical mean submitted by the agent. So there is no dependence on the variance of the data they submitted. Yeah, all right.
If I don't know people are truthful, then I'll not do that, right? I will not use that nice strategy. I'll use some bias variance trade-off to get a better estimator than this.
What do you mean by obtain a better?
Maybe like let's take it off.
Okay.
Take that at least.
Okay. Yeah. So I think that's a third paper. Yeah. So I was trying to come up with a summary of this tutorial, because I felt like the works in this area are very random, and people don't really have a unifying model of the problem, and also there is no principle for like solving this problem. So in the end, I feel like the only summary I have is that data sharing is a very complicated multiplayer game. It is very complicated because the strategy space for players can be very complicated. So far, we mainly focus on that the strategy space being the contribution level, but in the real world, the strategy can taken by the agents can be much more complicated. And also the modeling of the utility function is very complicated, because we care about the accuracy of the model on every agent, and usually it's hard to write the accuracy as a function explicitly as actions as a strategy taken by the agent. So which makes the modeling of the utility also very hard. And so in this tutorial, we just try to cover some simple but still very neat models of this data sharing games, and how could we apply the tools from game theory to solve it. Yeah, so these are some related work. I hope I didn't miss any of them, but yeah, but that's for it. Thank you.
So there have been questions throughout. But we also have time for questions generally about this area or more detailed questions. Yes.
Maybe sort of a general question. I'm curious how
Can I
this.
just pause for a second? Do I need to pass this? Let me pass this to you, and I'll take it.
Thank you. So I'm curious how this literature has intersected with the literature that's more on proper scoring rules, sort of Bayesian truth serum, which is sort of another set of techniques and models for how we elicit truthful information. Is that something you're familiar with?
Yeah, but I think there is, so far I wasn't aware of any work in this area like using proper scoring rules. I don't know, because the problem in the data sharing doesn't really have any nice structure so that we can apply the tools in that area. Because you could see that the utility and every modeling of this area is very subtle, and seems so far I didn't see like how to apply the tools from this area seeing this problem.
Yeah. No, I mean, I agree it's not exactly the same model, but somehow the types of assumptions that it seemed like you had to make in order to be able to do the elicitation sort of reminded me of the directions that we also go in this other literature. So I was just curious. Okay.
Yeah, I think conceptually it's definitely connected, but so far I think it's hard to say to see how to build little tools from that area to solve the problem in this area.
Yeah, Nika, it looks like you wanted to add.
I think my memory is failing me right now, but I feel like I've seen Yiling Chen give a recent-ish talk in the past few months where she brought these different things together. So there are works, and we do have this workshop, the third workshop of the semester, which is about agency and collaboration, and we'll probably have more of that coming in. But yeah, I also don't know. I just think I've heard Yiling talk about it.
Thanks.
Other questions?
So yeah, I guess I'm maybe wondering if you could say a bit more about what costs, like the cost of data sharing in this model would correspond to in reality in like some application domains. Like, is it just a metaphor for my apprehensiveness to sharing my private data, or like, is there some real like, tangible cost associated with sharing this data?
Yeah, I think for here we only consider a very simple cost modeling of data sharing that is just linear in the size of the data. And I know it's maybe overly simplified, but also I feel like it's a question like how to model the real cost in practice. I feel like in this area, modeling is really a hard question for every part. How to model the cost, how to model the utility is a question.
So I guess in reality, in these application domains, what do you think the real cost of sharing this data is? Is it mostly a privacy thing or like a coordination thing?
I think for here, I think we only mainly consider like just mainly focus on the data curation cost. So I think that is the simplest thing. I don't think this linear cost function captures like really capture the cost for privacy or security, as also just talked with Peter. I think he just mentioned like if we consider privacy, then the cost shouldn't be a linear function of the data size. So I would say this is very restrictive, and I think this might only be restricted to the setting about like curation. One data point will incur a certain amount of cost.
I see. And just so I understand, like curation means like the cost of like me pulling together all of my data from potentially disparate sources and making it available.
Yeah, or like you just labeling, because labeling a data point will incur some labeling cost, and let's say like so you have to hire some person to label the data, and so maybe you just pay the worker by like the amount of data they label, so then they will incur costs like linearly in the total amount of data.
But I guess if I was training a model only using my own data, wouldn't I still need to pay for the data to be labeled?
Yeah, because like I don't know, if you are Amazon and you want to train a model, so now you want to create data set, you still have to pay some workers to label the data you want to use, right?
Yeah, so I guess maybe that's why I'm confused, like, why this would be like cost considered specifically in the collaborative learning setting, right? If I have to label it anyways, you know?
Yeah, you want to incur this cost, but if you collaborate with other companies and you can split the cost, right?
Okay, maybe I'll think about it some more. But thanks.
Okay.
I had a more general question. So, do you know if there are applications where we actually see incentive issues in data markets in real life? Like, because often when I talk to people, especially like in federated learning, I hear the answer that, oh, no one's like actually even thinking about the incentives or strategizing. Like, you can come up with an abstract model, but no one's going to do anything. Like,
Yeah, because I feel like this incentive issues only appears in certain collaborative setting, like. Because if you consider the federated learning, like if I have a phone and my phone is like an agent, then I think this issue might not appear. And this might only appear like there are some big data collectors like a company or a hospital, and then I guess they might have incentives. But I just don't know if in practice they will really deviate, because I think usually they might sign some contract before they collaborate, and so they might also have some legal issues.
yeah, so that was like my next question. Like, actually, like, should we think of models where which try to accommodate the context that there's a strong penalty for lying or strategizing, so the agent also needs to make sure that it's not caught, not.
Yeah. So I just feel like in practice, like even in this kind of scenarios, like there are some more constraints on agents, like they just cannot, like, because due to legal issues, maybe legally they just don't want to fabricate data because they will have some additional cost because of that.
Yeah, because in your last example, for instance, like the mean estimation paper, like if there is a contract there, and like if I just catch you lying about the empirical mean, I mean, end of story. This, like, you violated the contract.
Yeah, but how to detect that? I feel like there is always like, I just feel like.
The same leave one out style thing.
Yeah, but I just feel like, if we guarantee this kind of not fabricating data by law, I think maybe we only recover the problem like after something happened, but after data leakage or after you did something illegal. So, but if you already have a data leakage and it has already caused some impact, so you still want to design some robust, some mechanism to guarantee that they won't do this. I don't know. I feel like this just solves the problem, like before something really bad happened.
But this is what law does, right? Like the law exists, you break it.
Yeah, the law exists, but law can only solve the problem like after something bad, really bad, already happened.
Yeah, I had a question about the protocol used in that third paper that you described. So is it true that I just want to sort of check my understanding. So in that protocol, was an agent sort of sharing its data based on whether other agents had accurately shared their data, or what was sort of the timeline there?
Okay. So I think if they believe that everyone else will truthfully share the data, then the best thing for them to do is also share their data truthfully. So it's conditional on some belief about.
Conditional on the prior rather
Yeah.
than what you actually said. Okay, I think that makes sense. Thanks.
No, I was just passing.
Okay. Any other questions? I guess more generally, you were saying one of the challenges in this area is that the works are kind of not part of the same way of thinking about the problem space. We also have open problem sessions throughout the semester, and if you were to tell us like one area which you think is the right way or a good place for us to be thinking about, what would it be? If you have one.
Yeah, to be honest, I don't really know because I feel like every model is motivated by some real world application scenario. And I just feel like, so far, I just feel like every model has its flaws and it's hard to see. And every model still has some gap to the real world model. So I think so far it's still hard to see like which model has more potential and is the right way of thinking. I think it's still a relatively new area. Yeah, but we will see.
Okay. Well, thank you so much for the talk. Let's thank Han once again. Okay, so now we have lunch on your own, and then we'll meet again here at 1:30 where Praneeth is gonna